You spend hours Googling which statistical test you use and you still have no clue? Tough luck. But here's the thing. You are asking the wrong question. Nobody actually needs a decision tree. What you really need is a clear formulated hypothesis, because a clear formulated question already contains the method. And I will show you what I mean in 30 seconds. Every student who has ever asked me which statistical test should I use got the same question back from me. What do you actually want to find out? The moment you can answer this question clearly, the test already picks itself. In this video, I'm going to show you exactly how you read your hypothesis correctly and can derive the statistical method based on that. The method is a consequence, not a decision. Here's the single most useful reframe in all of applied statistics for students. Choosing your test is not a separate step you take after writing your hypothesis. Instead, it is the end of a chain that starts with your research question. The chain goes like this. Your research question implies what you want to compare or what you want to measure. That implies what kind of variables you need to collect. And this already implies the structure of your data. And the structure of your data combined with the research question, this already implies which test you should use. It's a chain of consequence, not a choice from a menu. In my last video, I showed you how you can derive some methods from your hypothesis and how you state the right hypothesis. And now we will look at the same hypothesis again and try to get to the method from there. If you do not know how to state a clear and precise hypothesis, look at the link below. All right, so this is the hypothesis. Students who exercise 3 times a week report lower stress scores on the PSS-10 scale compared to students who do not work out at all. This sentence already contains a dependent variable, the thing we want to measure, the PSS total score, and it already contains a grouping, students who work out and students who do not exercise at all, group 1 and group 2. These groups are also independent, so people who exercise cannot be the same people who do not exercise, so we have different people who are testing against each other. And we also have a direction. We suspect that people who exercise have a lower stress score, so we also have to consider this in our statistical method. So this, what I showed you here, is like 90% of everything you need to know in order to pick the right test, even before you have to look at a decision tree. Can you guess what test should be used for this hypothesis? Comment below if you have an idea which test is implied in this statement I showed you right here. We will come back to this later. So let's make this more explicit with 3 questions. Not as a checklist, as a reading exercise for the hypothesis you already have written down. Question 1. What type of dependent variable do you have? Can I do calculations from it, like a PSS-10 score or your GPA? Then we're talking about a metric dependent variable. On the other hand, we could also have category, like a group, a yes-no question, or a label, whether someone is employed or unemployed. In this case, we're talking about categorical data. As our PSS-10 score is metric, so we can perform calculations with it. You can average the scores, for example. Then that's a metric independent variable, and this is the first thing we have to consider when we want to talk about the implied method. Question 2. If you have groups, how many groups are we talking? Are we talking about 1 group, 2 groups, 3 groups, or more? And are we talking about different people who are compared to each other? Or are we talking about the same people? For example, you have week 1 test the people and week 2 you test the same people again. In the study I've presented in the first video of the series, where we prepared the data for the analysis, there we could see that we have 61 students who exercise and 60 students who do not exercise. So we're talking about different people, so independent samples. So as we have independent samples, metric dependent variable, and only 2 groups, this heavily implies independent sample t-test. That's not a conclusion that resulted from a decision tree. This conclusion already sits inside of your hypothesis and just waits to be read out. Every time you see a decision tree, it's more of the drawing of a process which more or less reflects your own hypothesis you already have written down. Now, let's do another example. A higher sport frequency is associated with lower stress scores on the PSS-10 scale. So let's start again with our dependent variable. The dependent variable in this example is again the PSS-10 score. The second thing we're looking for, are we talking about groups? In this hypothesis, I cannot see that there are any groups mentioned. We are talking the same group. And the data type we are talking about, higher frequency in sport, means lower stress scores, so we have frequency, and the stress score, so we have two metric variables where we're stating association with it. As we're talking about relationships, you can comment down below what you think which statistical method is implied. As you see, this is a completely different hypothesis structure. In this case, we are talking about a correlation. And this is just because the hypothesis you've already stated is formulated in a different way. And you also want to find out a different thing about data you have collected. Before we go deeper, I want to show you the full map of statistical tests. And we go back to our examples. If your hypothesis compares groups and the dependent variable is metric, so you can do calculations with it, we're talking about the difference test family. And within the test family, we have to differentiate between two main groups. The first one is the group of the t-test family, and this is where you only compare two groups with each other. If you have more than two groups, ANOVA is the right test subfamily in this case. Two groups, t-test, more than two groups, 3, 4, 5, 6, ANOVA, always. If your hypothesis describes a relationship between two variables, not between two groups, that's the relationship test family. Within the relationship family are two very similar methods. We're talking about the subfamilies of correlation and regression. The regression is the more complicated one because in this case you do not state there is just an association. Instead, you're trying to predict the outcome based on the variables you have at hand. 5 variables try to predict our outcome, for example, stress level. You can predict the stress level based on sleep schedule, workload, and so on and so on. Then we're talking about regression. If we're just talking about the relationship between two single variables, we're talking about correlation. In the case you have two categorical variables and you're stating that there is a relationship, then you're not in the pure relationship test family, you are in the frequency test family. Because you can only derive anything by counting, for example, sport, no sport, stress, no stress. So you have to count how many people are in which group. This would be the chi-square test. Each of these tests will also get their own videos, but for now you only need to know in which family you're in, difference, relationship, or frequencies. And that again comes straight from the hypothesis. The full table in the decision tree you need to know in order to pick the right statistical test. You can find a complete guide on Statoria.com. I post the link in the description below, and there you can find the full guide on how to pick the right tests. Alright, let's go back to our main topic. This concept is something no one will tell you in your statistics class. The concept of target tests and when you should switch to different test choices. Every statistical test has assumptions. These are conditions that need to hold in order for the test to be valid and to give you a very precise and very good answer. If these assumptions are violated, you don't need to abandon the ship immediately, but there are alternatives you can use in order to get to a not disturbed answer in your test results. It's the last branch you take in the decision tree. Do I keep my target test, or do I switch to a different test within the test family where we do not have to fear that there are disturbances inside of the dataset? So for the t-test I've mentioned before, several assumptions, but two we really have to look out for. The first one is the normal distribution. The scores within each group should be normally distributed, or at least the errors within these test scores. Normally, to save some time, you only test the groups itself. So you can test this by using a test called the Shapiro-Wilk or Kolmogorov-Smirnov test. So when you think this sounds very complicated, I have a good message for you. There's a very practical shot. The t-test is very robust against the violation of the normal distribution assumption, but only if you have a sample which is above 30 people. So if every group has more than 30 participants, then I can still use the test without a problem. This is called the central limit theorem. The main problems you have to look out for is when you have very small sample sizes below 30 per group, because then you really have to look out for outliers or different things that can really disturb your analysis. Second most important assumption for the t-test is the homogeneity assumption. So the idea that every group has a similar spread within their samples. So if, for example, if the people who work out a lot scoring very narrowly in the PSS score, while the ones who do not work out, the scores are all over the place, then you would see this assumption violated. Most statistics programs using something that's called a Levene test. And this tests exactly how big is the spread around the mean value. If this assumption is violated, then you do not use the t-test in its purest form. You have to do a correction, and it's called the Welch test. Because this is a very frequent matter, most tests already give out the correction. The full decision path I took for my first hypothesis would look like this. So the target test of this hypothesis is the t-test, metric independent variable, and we have two groups with different people in it. If the sample size per group is big enough, then you can just go up and follow the path above. So you just look with a Levene test whether you have rather equal variances in your test groups, and if so, you can use the t-test. Otherwise, you have to perform the Welch correction. Very simple. If the normality is clearly violated and you have a rather small sample size, then you should consider switching the t-test to a non-parametric alternative. This would be the Mann-Whitney U test, which works with ranks, so it corrects for outliers and such. I already have per group more than 30 people, like 60, which is big enough so I can, the normal distribution assumption is violated. I can still use the t-test and I will find good enough answers for my hypothesis. The other hypothesis, the correlational one, follows a similar logic. The target test for this hypothesis, the Pearson correlation, because we have two metric variables and a relationship question we want to answer. Both variables have to be approximately normally distributed. So we have to do the same check with the Shapiro-Wilk test. And the second assumption is that we have a more or less linear relationship. So if we plot this like this, we should expect that the data behaves in a more linear fashion and not like in a pattern like this. In this case, the Pearson correlation would give you a little bit too low correlational answers. The scatter plot I draw here, this is the same you should do with your correlation so that you can really see whether there is a real linear relationship at hand. If either assumption fails in that regard, switch to a different type of correlation. For example, the Spearman correlation. Especially when the normal distribution fails, you should switch to the Spearman correlation. Like the Mann-Whitney U test, the Spearman correlation also works with ranks, so it also is not that susceptible for violations against the normal distribution. In the dataset I used throughout the series, both variables are metric, the sample size is well above 30, and the scatter plot between sports and frequency against PSS shows a clear downward trend in a rather linear fashion. So Pearson it is. Now you know when you should switch to your non-parametric alternative. Alright, I've talked to you well above 10 minutes right now. Pause the video here and run through the three questions I mentioned before. What type of dependent variable do I have? How many groups do I have to consider? Is it 1? Is it 2? Is it 3 or more? And am I testing the same people or am I testing different people? If I have just one group, what type of relationship do I want to see? Do I have just a relationship between two variables, or do I have a relationship between one variable I want to predict and 5 variables which should be associated with this prediction? In this video, I only showed you the two most common tests used throughout every student's thesis I've seen so far. There can be even more complex hypotheses where you test groups and effects at the same time, where we try to get interactions between different effects and so on and so on. So this is something I do not have touched in this video so far. You can comment down below. As this series will go on, I will catch up to these topics. So in the next video, we will perform the t-test and correlations. We will look at the statistics and we will try to interpret what you should look out for and how you should present this in your thesis. So keep watching, subscribe below, leave a comment, and I see you in the next video.